All right, I'm Dave Cedarberg. I'm the outreach coordinator for the Department of Physics and Astronomy at Purdue. And Christopher.
Hi, I'm Christopher Romley. I'm a professor at Westchester University in Westchester, Pennsylvania. And you're probably wondering, how in the world do Dave and I know each other? Well, I got my PhD from Purdue in 2017. I was in the Earth, Atmosphere, and Planetary Science department. I was getting my degree in Earth Science Education. And prior to this PhD journey, I was a classroom teacher in New Jersey, North Jersey, for 15 years, teaching high school and middle school science. So I just want to kind of give you a little background on the origin of lazy days. When I started out teaching 25 years ago as a public school teacher, and I was coming up on, I knew that I had to teach motion and Newton's laws, and I'm like getting ready to do something for, start with the Newton's first law because that's first. And I'm like, all right, what's the lab? There must be a lab. I was a brand new teacher. I was actually an alternate route teacher, so I didn't go through a formal teacher training program. And so I'm like looking and I'm like, there's got to be something. What do they do to understand it's motion. They must do something. And I was really disappointed that there was no activity or set, and there was we were just kind of still learning what a web search was, and you type in Newton's first law, an old Netscape, and try and find something in the early internet or youthful internet, and there was really nothing out there. There was some activity that involved 2-liter bottles, a weaving hoop, and bolts. And I was like, oh gosh, there's that's just not going to happen. And it was just I was just like, well, we got to do something. I got to think of something. And, you start looking a little further and a little deeper, and you realize, well, this is something that students could do to demonstrate and physically be a part of an action that is all about and happens because of or is related to Newton's first law. And you start, oh, well, what about this? And then what about this? And then what about this? And then you slowly build up these demonstrations or tiny activities. And I'm like, you know what, maybe we should put them all together. Maybe if I put them all together and make it like a stations kind of activity where they go from one station to the next, and they are they're doing some physical action, some task. And they have to try and figure out, well, how is Newton's first law involved? Once they're given some background on Newton's first law and what that is and all that it entails, how is Newton's first law involved? And so it originally evolved from just a very informal 3 or 4 or 5 stations, and then it became a little bit more formalized with 6. And then, over time, by the time I was in my 10th or 12th year of teaching, suddenly I had 10 to 12 or 13 stations of all different kinds of activities that students are demonstrating or going through this process and demonstrating aspects of Newton's first law of motion. And I have demonstrated. And then when I got out to Purdue and I met Dave, and I was like, well, maybe this needs to be published, because wouldn't that be great for both of us to get it actually published in a teacher's practitioner journal. And so we collaborated on a article together that describes the genesis and the need for teaching and the need for the why these stations and how each of them is related to Newton's first law. So that's where kind of the short story. It was kind of built out of frustration that there wasn't any real good activity that took the kids through literally the motions and where they got to. I mean, if it's Newton's first law of motions, they should be up, they should be doing things and at least that was my philosophy. It still is my philosophy that if you're going to be teaching Newton's laws, that they should definitely be active, and it should be a very kinetic and kinesthetic type of activities. And the stations, I've always been a fan since my first year of teaching, been a fan of stations, activities that involve stations. And this does involve a number of stations where they get to experience and see, and both also they personally can be a part of that first law experience. And to me, that was extremely important. So the man himself, blah, blah, blah. By many discoveries, more paid attention than to any other talent. And I believe Newton also talked about standing on the shoulders of giants, which is also attributed to Galileo when he was talking about Bruno and Copernicus. So different people are related to that expression. How come my clicker is not working? There we go. Anyway, where this all fits in with next generation science standards, we often hear this expression, three-dimensional teaching and learning, and what that entails. And well, we want our students to be doing science. We want them practicing the skills that scientists are engaged in, that they're actually doing science, that a science lesson, whether it's a full-blown investigation or it's a day or two or three doing lazy day stations, but even just our direct instruction kind of days still involve those skills that scientists are practicing. And so we want our students to be doing science. That term phenomena-based learning, phenomena-based investigations, and students are trying to figure out and make sense of a phenomena. Well, there's certainly a phenomena when it comes to any of these stations, but if the phenomena is just kind of generalized as Newton's first law, then certainly we can see what that's all about. And certainly Newton's first law of motion definitely has real world applications. While the stations may not seem so real world, they seem just kind of like a fun carnival atmosphere, but Newton's first law definitely has real world applications. And they can solve some problems as well as they go through this. Three-dimensional teaching and learning. I like to use a cake analogy. I like to cook and I like to bake. And those of you who know, that is the Barefoot Contessa and Ina Garten. She is one of my favorites to watch. And so is her food. It's really good too. But if we think of cake and the three dimensions as the cake being the core idea, the definite content, the concept that students are learning, where the practices and those process skills are all the different tools, the sifters, the mixers, the measuring cups and spoons and whatever else we're using that we need to make a cake, as well as the frosting. And the frosting is that cross-cutting concept. What's poured over all of this and holding it together and enveloping the concept itself. If frosting isn't doing it for you, perhaps you can envision the cross-cutting concept as a thread or a superhighway, because that's how we can get from one to the other. Our science and engineering practices, if you're familiar with NGSS, you know that these are the 8 SEPs, SEPs, and we like to see all of these or some of these, a few of these, not just in a big investigation or on a lazy days, but also in any type of individual, more direct instruction lesson. We can still incorporate these in our lessons, our daily lessons. And those cross-cutting concepts, the 7 cross-cutting concepts, these are how we frame, which is another analogy if you prefer pictures and art. How do you frame your lessons? And the cross-cutting concepts help us to do that. It helps us direct the learning, and it helps us students to kind of, with their conceptual understanding of the phenomena that we are intending to teach. And so, and not every, some people could see lazy days fitting into different cross-cutting concepts, or the cross-cutting concepts that applies to lazy days or a unit or a lesson on Newton's first law could be different depending on that teacher's approach or how they envision what they're doing to teach that particular concept. So let's take a little journey about Newton's first law. And I want to keep this relatively short because I want you to see the stations, because that's probably the more important part of this. But Newton's first law, if we started off here, or if we kind of bring this in a little bit later, I think most people know the object at rest stays at rest, the object in motion stays in motion. And then some people kind of just stop there, but there's actually another really important part to a clause that's often left out or that kids don't remember, and it's that unless acted upon by an unbalanced external force. And that question or that unbalanced and external force is actually really important, and we like to bring it up during lazy days or as the students are going through the different stations to kind of remind them about the forces that may be involved, that may unbalance something and that are external here. Well, we could start off with a question, which is a nice way to start off any lesson. If an object is still and not moving, how do we get that object to change its condition of rest? If it's at rest, what do we need to do to the object to change its condition of rest? And the student might say, well, you could take a chair and, how do we get the chair to not be moving? How do we change from its condition of rest? And we might say, well, we got to push or pull it. And what we're really talking about is applying a force. So forces are involved. And the same thing, well, if it's moving, how do we get to change its condition to get it to stop moving? And that also involves a force. And that leads us to, well, what are those forces that can change the motion or the lack of motion of an object? And oh, my student teacher wants to answer that. Or excuse me, my former student teacher wants to answer it. Rhetorical question. Not really rhetorical, but it's something that we could ask. What are those forces that can change the motion of an object? Well, students might come up with gravity, because that's a pretty familiar force to them. By the time they reach a certain age, they're familiar with gravity being a force, so they may come up with that. It may take some kids may come up with this actually first. Friction may come up as being a force that they're familiar with. Magnetism is a force. Electricity is a force that changes the object of a motion. Certainly magnets are a great tool to demonstrate how we can change the motion of something like that. When we just flip the light switch on and off and talk about moving electrons or not with electricity. Some students might actually say air resistance, and that's certainly valid in this case. We like to take all responses for that, and it gets us thinking about all the different forces that can be involved in motion, getting something to move or changing something to move. Another concept is mass and the difference between mass and weight. And we could just have reminders about that and how to calculate the difference between mass and weight, especially when we're going into kilograms, because we like to use scientific measurements, especially when we're doing any kind of work with Newton's laws, especially as you move from into the second and third law, where calculations and formulas become probably more common when you're getting into the second and third laws. So what does that mean in relationship to not the National Football League, but Newton's first law? Because, got to abbreviate it and make it kind of funny, NFL. So any object of any mass is going to keep on doing whatever it was doing, unless there's some unbalanced force that changes it. So if it's sitting still, it's very happy staying still. But if it's moving in a certain direction at a certain speed, it's very happy doing that too. And it really doesn't want to change. In fact, it won't change, especially if there is no force to come and change the motion of that object and make it change its motion. So another word that we would incorporate here, the word acceleration. So that's the change in motion. So what do we mean by unbalanced and external force? Well, I'm gonna go out of screen sharing here because I have a chair here, and my Christian, my friend here, is happily sitting in the chair. And the chair is not moving, but if I ask him to, without touching the wall and without touching the floor or any other object, and just sitting in the chair, so he's there in the chair, can you get from here to the far side of the room without touching anything? So try and move yourself. It's a rather creative way to try and do it. A little hard there. Yeah, that's going to be quite a long journey, but it really is quite difficult to, because he is his own system, and being in the chair, and he's not allowed to push off anything or pull anything, and he's trying to kind of pull the chair or almost lift it up, and he goes with it a little bit. If we didn't have wheels on the chair, that might be even many times harder, because then it doesn't have the ability to roll. But if I go over there, I can push him with relative ease, and he moves with relative ease. And that's because I'm the external force that's providing the change in motion. So when he's at rest, he's at rest. If he tries to move all by himself without pushing or pulling off of anything, it's close to very difficult, if not impossible. But if I come in to push him, then he can move along. So, all right. So that's that unbalance and external force. I provide that unbalance or imbalance to do so. And a physics book is very happy. It's balanced, sitting there alone on the table. There's nothing going to come along and change. Gravity pushes it down. The table pushes up. It's equal. It's at rest. But if I come along and push the physics book, then it starts to move along. And so there's always some kind of unbalanced force acting upon an object, especially if it's in motion. And on Earth, those are going to be friction and gravity, because you throw a ball up, it comes down. If you take that physics book, or if you try and, if I push the chair without any tables or chairs around, and I pushed him, eventually he would slow down and come to a stop. And that's because of the friction between the chair and the floor. And we kind of just forget about magnetism and electricity. They're also move things. But in terms of lazy days and these activities, it's going to be friction and gravity that do the changing. So if we're in outer space and we're far away from any other object, we're away from the gravitational pull of Earth and the moon and Mars and Jupiter, and we can get far enough away, that rocket ship or that satellite, whatever we send out, that's going to keep on moving at a certain speed in the same direction forever, unless it happens to get close to some celestial body. If the rocket is not moving, if the space shuttle isn't moving, then it's not going to move unless there's an unbalanced and external force applied. So if it's not moving, it's very happy not to move. And if it's moving at a certain speed, at a certain direction, it wants to keep doing that. It does not want to change. Just like the thing that is stationary does not want to change. Essentially, it's kind of like nature is lazy. It just resists change and just wants to keep doing what it was doing. And so hence with that comes the idea of lazy days. So I'll talk about these a little bit later at the end, and all the applications to NGSS. But Dave, I think we want to spend some time with these stations.
Just want to mention to everybody with us We have everybody's name in a dish. And we're going to pull out names. If you can stick with us at the end, we're going to pull out 2 names. And if you are here and respond, we will send you free of charge to your classroom or whatever address you specify the Lazy Days materials to do this, these stations in your own classroom. So just to give you a kind of a bird's eye view, this is, well, there's Mitch. He's one of our volunteers. We've got stations set up around the room. This is just a typical classroom, laboratory classroom. And we're gonna just start with the stations and have my student volunteers show you what to do. So let's start with my cup runneth over, shall we?
Oh, okay. Well, you're starting off hard.
Faith has in her hand a cup of water that is full to the brim. Now, if I were doing this in a classroom, this would be a timed activity. Kids would go around in groups of 2 or 3 or 4 to each station. And in this one, it's a little competition. We would give one of the students a stopwatch to time the other team member in how long it takes them to go around the cones, holding the glass of water without spilling it. Faith, come on, go fast.
A lot harder than it looks.
So I know when I've done this in my own classroom, if you don't have the little cones, which are great for lots of different things, you can just go around the perimeter of your classroom, depending on how it's set up. If you do have cones, it might be good to put tape on the floor with arrows, so they know that whether they have to go to the left side of the cone or the right side of the cone. And the important thing is that they should be watching the cup, which is filled to the rim with water, how that's behaving. And their colleagues, their team, small team, who's ever timing or who's ever observing, should also watch whoever is going through the maze, because the student with the cup of water is probably going to behave a little differently as they change direction, because they don't want to spill the water when they're turning from left to right as they're going through that little obstacle course, or they're going around in a square, or whatever their shape or pattern that you have set up on the floor. So the student with the cup is also not just being aware of what the water is doing, but they should try and be kind of present in their own body and be thinking about, how do I move? What do I need to do so that I'm not spilling water? And how is my body behaving as I'm moving around this obstacle course? And the students who are with that, in that team, that cluster that is at that particular station, should be watching closely, especially the changes in direction. That's key as well, because the behavior of the student with the water will most likely change. It's very hard to maintain that speed, changing directions, and also to prevent water from coming out, because the water wants to just keep going in the direction that it was, right? The water was happy in the cup, it was going in that direction. Suddenly you have to change direction, almost make a 90-degree turn. How do you do all that and allow the water to not spill over? The water has to kind of also change direction. It's kind of lazy. It wants to keep going in the direction that it was. So did another student want to show how they do there?
Yeah. So let's have Meenakshi do it, and watch her body, watch the cup as she comes through the obstacle course, moving as fast as she can.
Oh, they got to go back. Wow. Dave's tough.
Man, I just totally spilled it there. All right.
So different students will take slightly different approaches. Their upper body and lower body may be doing almost different things, how they're holding their hand. But we like them to kind of hold it kind of almost at eye level, where the top of the cup is at eye level, definitely at shoulder level. So they are kind of, they're not only kind of watching their path that they have to go, but they're also watching the cup.
We are set up to do station 4. We're going to demonstrate how to do the domino effect. Now, you know, part of the fun in doing this in a classroom is figuring out, number one, what works best and what you can do to help your students be successful. Goal will be to knock the dominoes from the bottom one by one without knocking the stack over. Christopher, let's see your setup.
Pretty similar. So the shoebox is here, and it's taped down to the table, and then you can stack as many dominoes as you like. I think I found this. I'm not endorsing any product, anyone. So it's just if you find these, I think I got these at Target. Well, you know, it's a fancy store. So that's what I have. So they're the white dominoes, and I've always found that a wooden ruler works best for this because you want something nice and relatively sturdy. A metal ruler would also work. You don't want one of those kind of bending, flexible rulers. It might not be make the right impact in order to get the dominoes to move from the stack into the shoebox. And the only slight potential hazard is a ricocheting domino. And that's okay. And try and figure out, well, how do we actually hit it? You know, what do we have to do in order for just the one domino to leave the bottom, and so that the rest of the dominoes just fall, because they're just falling in response to the gravity. Let me see if I can still have my old sharp technique there. I cheated. Right. Kids will try and set all different kind of records with this, and they'll try and make a stack of 20. The other thing is that when they do make big stacks of 10 or 15, they can readjust the stack to make sure that the dominoes are a vertical stack if they start getting a little off.
We tried a different kind of domino as well. We found some that were much cheaper. They're a little bit lighter.
Cheaper than Target?
And I think they're wood, but they behave a little differently. Alan, see what you can do. Okay, so
fall over a lot easier.
They fall over more easily, but they still work. Shall we move on to the next station?
Sure. Where are we going?
I think we're going to do tennis. Anyone?
Oh, okay. So it's just a ball with some string or yarn or twine, so you kind of make like almost like a pendulum effect. And this one takes a little practice, and you always want to do this perhaps in a long or empty hallway as a crowded classroom, because if there's 20 other students in the classroom at other stations, you probably don't want to have a flying tennis ball. And so we just want to get the student kind of getting the tennis ball in a circle, spinning it in a circle. And then the trick is for them to release it at the bottom of the arc or the very top of the arc in a direction that is not toward me. Yeah, okay, thank you. Or toward the eggs. And the trick is for not necessarily the student who's actually holding the tennis ball and maneuvering the tennis ball with the string, it's the other students who are watching. They are not just passive observers. What the tennis ball should be doing when it's released at the very top of the arc and the bottom of the arc is that it travels in a straight line. From the point of release, it travels in a straight line. And then eventually, in a few tenths of a second, it falls to the ground. Gravity takes over. But for that few moments after the release at the top of the arc or the bottom of the arc, it does travel in a straight line because nothing is keeping it in the circle anymore. So we want that ball kind of moving outward in a direction from where they are releasing it. But it's really important. It's probably more important for the students who are watching the station to watch what the ball is doing. It's not so, we want the person who's twirling the ball, tennis ball, to make sure that they're releasing it at the top of the arc or the bottom of the arc. But it's more important for the observers to be active observers and be drawing what they're seeing. How does the ball move immediately after it's released? Better one. Yeah, definitely a good one. So I think there's somebody in Dave's room who's got it there. Dave?
We do it in a circle overhead because then the only force acting on it is, well, in either case, it's gravity. But the point is it's going to go in a straight line. So Emily, whenever you're ready, I'm ready.
Okay, I'm afraid to hit the camera.
Yeah,
But
just don't. Easy enough.
just don't.
I just got that in case I put the camera
Okay.
attached, you know.
Okay, cool.
All right, Emily, go for it.
Ah!
Okay.
Okay, well,
So we can see what happens with an early release and how it should have gone toward Dave in the camera. But I like the idea of a target somewhere in the wall, in the hallway or the room, so that they know that their release should hit the target. And that gives them, and that may give some guidance for that particular station. So a target is on the wall is actually really quite good because then they know they have to release it so that it gets to, train gets to that target. You probably want to keep them closer to the wall as well. So it would actually make a straight line from the release point to that target on the wall. So that's actually a really good idea to have a target there. And it looks like Dave is going to, where Dave? Is that Cup Tower?
Yeah, let's do Cup Tower.
Oh, where I was before, okay.
Do you want to give it your shot first?
Yeah, so your red solo cups, some laminated index cards or cardboard will do. And, oh, my God. So we have a stack of cups now. With this, they could stack the cups in any which way they want. They could be mouth side down, they could be mouth side up. They could do 2 cups at each interval. It's up for them to decide, but they're also going to start thinking, wait a minute, maybe if we had more cups on here, more cups equals more mass is more resistant to movement. Would it be easier if we stacked 2 or 3 cups in between the cards and that adds more mass and they won't move as much? So now they're starting to think with these stations about how mass is involved and how more mass is more resistant to movement. And it might be easier if with a whole bunch of more cups in between, but they also figure out a way to remove the cards so that the cups just respond to gravity, just like the dominoes, and just move down and pile on each other. So, and every student finds a different technique. Some like to flick the card out, and some, Christian, I don't know what your particular technique is.
We had that one before.
Should we try 2 cups or should we
Go
try?
for it. Oh, I had that.
And then there's the grab. Oh, almost. I will say that this is probably the most challenging. Oh, to go. Yeah.
There.
Probably one of the more challenging stations.
So try to see what happens here. Nope. It's hard.
I'm gonna fail miserably, I'm sure. And just because I'm the teacher doesn't mean I get to do it. Right? This was actually one of the stations that another student devised. So one of the ways to assess what they get out of lazy days is for them to create a new station using basic materials, not like, oh, get in your car and get a big truck and move this or something like that. It's something I said I can buy at the ShopRite, dollar store, Target, whatever. And the student actually came up with this particular station. It was index cards and red Solo cups. And I said, I think I might make this like a permanent fixture in the lazy days. So, and again, they think, you know, multiple cups in between. Is it mouth side up or mouth side down? What works better? What's easier? What's the technique for getting the cards out from in between? And all different kind of techniques with that. So Dave, I don't know if your students have something else.
Well,
with that?
sure. We have the same station set up. Mitch, come on over here. So Mitch is going to, we've tried today some different kind of cups. We tried the red Solo cups, which we've always used. And today we tried some clear plastic cups, some clear cups, one of which has a wider rim, which might make them easier to stack for the younger students. But Mitch has some just like normal, I don't know, clear cups here. Mitch, let's see what you can do with those cups.
How many did they get in a row? Did they get all of them?
Well, let's not point the finger at the competition, okay?
All right.
I just got it. I just got it.
Oh,
There.
okay.
Oh,
Well, all right. So some students will try flicking with the finger.
Mhm.
Others like to pull. And if you push or pull, I mean, your hand actions are all, it depends on the person. So,
But it has to be quick, obviously, right?
yeah,
Because we
yeah,
want
you have to be quick.
we want that card out of there so that they just respond to gravity.
I like your suggestion, Christopher, about having the cups maybe stacked in pairs or groups of three.
Yeah, right. More mass.
Especially with younger kids, that works
Mhm.
really well.
Mm-hmm. Well, it worked with me, and I'm not young, so.
My next activity set up here is Eggsellent.
Oh, excellent.
Should we do Eggsellent?
So we got some eggs here. And I'd like to put them on their own plate, but there was only one, amazingly in our office was only one plate. But it's nice to put them on their own plate and with some laminated directions, do not pick up. And I usually like to put out probably either 6 or 8 eggs. In particularly adventurous years, a whole dozen. You got to know your audience, right? But they cannot pick up the egg, but they have to try and figure out whether the egg is raw or hard boiled based on some physical characteristic that where they can't pick up, but they can touch, but they can't actually pick it up. They can't crack it open, they can't open it or anything like that. So they have to try and come up with a technique in order to figure out which eggs are raw and which are hard boiled. Now, some of you may already know this trick. You do, yes, of course. And so we have an egg here and we just, eventually they'll figure out that if we spin it, that an egg that just kind of spins really nicely like that one. And then there's this one that just kind of, no, that's actually not bad, but it does wobble. Well, there it goes. It's just kind of wobbling around and certainly not at the speed that this one gets. And it turns out that if this is the raw egg and this is the cooked egg, well, you have some, you have liquid in here, which is moving at a different speed than the shell. And liquids behave very differently when they're in motion compared to a solid. And so you have a different, very different observable behavior in a raw egg, as opposed to a cooked egg where everything is solid and it just gets to spin around as one cohesive unit. But they'll try all sorts of things, including smelling. And I'm like, well, how would smelling, relate to Newton's first law? But we like to try and eventually they'll figure that if they spin it, they can figure out which eggs are raw and which eggs are cooked. But you do get accidents no matter what. And but if the worst is a raw egg that ends up on the floor, then just it's pretty easy to clean up. Are they spinning there, Dave?
Yeah. So I have Ravi Shankar with our setup here. I'm going to point out. I don't know if you mentioned this, Christopher. It's really important. I always duct tape the plates.
Yes. Oh, yes. Sorry. Yes. Good idea. The plates, tape them down to the right, so they actually can't lift up the plates.
Sometimes when students spin the eggs, they end up knocking the plate off on the floor. And so taking them down is good. I also set out picks and I number them. So when they're taking notes in their journal or their notebook, they can write down which numbers behave accordingly.
All right, we're off to next.
How about red light, green light?
Okay, well, you guys are going to play that because it's just us here.
Okay, then.
Well, I think this is probably everybody's most favorite station because it's like your old childhood favorite game of red light, green light, or Mother May I, or TV tag, for those of us that are, used to play that back in the day. But red light, green light, some kids do not know this. Some of my method students have to be introduced to it for the first time. So, it's just a matter of the kids who are trying to get to it, whoever is the caller, who is facing, so they're all facing, they're on one side of the room or in a hallway, if you can do this in a hallway, especially where there's not colleagues, or at least you can tell them, hey, we're going to be having some kids in the hall playing red light, green light. But if you're doing this in the classroom, the students, it looks like we got 4 people on one end who are ready to head to Dave, who might be it. And Dave is going to would face in the opposite direction from them, or actually in the same direction that they are. So he doesn't see them, and he's calling out 1, 2, 3, and then does a quick turn red light. Now, what he's doing the call of 1, 2, 3, there's at moving forward at different speeds. Some kids like being like the tortoise and slow and steady wins the race. And some people like being the hare and will dart out forward. However, of course, if Dave turns around and calls out red light and that student is not stopping, has not stopped when the red light is called, things tend to happen with a student moving a little too fast when there's a red light, just like in real life when you're driving a car. So I don't know, Dave, did you want to play this for everybody?
Yes, I'm going to count just a couple of stops and starts so that people can see the motion of the body, the momentum.
And that's important too for the people who are playing and the people who are observing, is to be active observers, to note how the bodies are behaving when red light is called. And what are the bodies doing at that moment the red light is called? And to maybe focus on 1 or 2 students of moving rather than a whole group of students moving. Go ahead, Dave.
Green light, red light. Green
Yeah,
light,
she needs to go back.
Yes, you guys.
Okay, you got the idea.
So there's different call sequences. Some people do green light and then suddenly red light. Some people do they're turned in the other direction and they go 1, 2, 3, red light, and they turn around. Or you can really throw people off and say yellow light, and then see what happens. But of course, with red light, green light, if they're caught moving on red light, we want students to observe that motion. Some students do, that kind of falling over action. And that's because they haven't stopped. They have that momentum, which is kind of related to, Newton's first law, that their body is in motion, that it's very happy moving forward and it doesn't want to stop so easily and quickly like that when they're in motion. And we think about all the different other variables that could influence whether a student continues to move forward or not when they're playing red light, green light. So that's always a lot of fun. But the important thing is to be the active observer of the body and what's happening to the body as red light is called, and why does it continue to move forward. And everybody likes to get a turn, everybody likes to be it, and everybody likes to play. So it's to allow enough ample time at each of these stations that we've been showing to let the kids experience that, because we want them to experience that momentum and their resistance to stopping when they're hearing red light and they suddenly have to realize, oh, if I don't stop, I'm going to have to go back to the starting line, which is kind of like what happens when you get caught on a red light and you're still moving, you have to go back. So
What I have next here, Christopher, is my favorite station of all, and that is Water World.
Oh, you have the best Water World.
So we've got
Have the alternative Water World. Dave has this great contraption which works for Water World, and not world as in W-O-R-L-D, but world, W-H-I-R-L-E-D. So whirling water around. So you can see Dave's contraption is some string with a little platform, and there's ability to put a cup on that. And eventually that whole apparatus will get whirled around. But if you don't have that, although the lucky winner of the, I was going to say 50-50, but it's not the 50-50 of the raffle at the end. If you don't have that contraption, or you will if you win that, the next best thing is a bucket. And you can do this with a bucket and whirl the bucket around. Yeah, you can do it right here without hitting any ceiling light fixture. Or not. Well, now we know. So we're going to try and figure out the light fixture here. Dave, you better go.
No pressure.
okay.
No.
All right, so I have Alan and Emily here with the apparatus, and I'm going to post a video in a Google folder with everything from today, including a video of how to make these devices. So let's, we're getting short on time. Let's see you do it. Go.
Wow.
Of course, the hard part is stopping, but success. All right, so there's Water World. I have found that the cheap and easy one there is the foam board with just string drawn through on the corners and tied a knot. I do put a felt pad on the board to keep the glass from sliding around a bit, but there we go. Christopher
Will do as well if you don't have that apparatus.
Sure.
And just be careful of light fixtures. We're all good here.
Okay.
They're still working. Yeah, they're fine.
All right then. So let's. We're going to go to catch that quarter. Is that okay?
Sure.
All right.
So all you need is a quarter or a whole bunch of quarters. Just go to the bank and exchange a $10 bill and get a roll of quarters. And it's pretty simple. You don't need anything else but your put the quarter on your forearm, and it's like those old trick, and you just release your forearm and you can catch the quarter. And of course the goal is to catch it before the quarter actually starts to think, there's no arm to support me anymore. And before that quarter starts to respond to gravity, which is now the external force that's going to change its motion because it was at rest, except that the arm isn't there anymore. And now gravity is going to take over control of this quarter's motion. and you reach in and grab it. The important thing is that to show your students to just drop their forearm and catch it, and not actually, some students will actually start and push and actually toss their arm up so that the quarter starts going up. But we just want to drop our forearm out and catch that quarter. And I think we have some attempts going on in Dave's room. Looks like some very successful attempts. And of course, we always want to provide a whole bunch of quarters, because does more mass from more quarters actually make this task easier? Because more quarters, more mass means more inertia, more resistance to motion. Does it make it easier to catch? Although, of course, some of the factors is like how big is your hand in order to catch a hand 5 or 6 or 10 quarters. Although I have seen 13-year-olds catch 18 quarters. So that was pretty impressive. So, how do you do with this?
How do I do with this? I go like this.
Oh, wow. Way better than I am. Oh, he's going to try 5. He's going to show off here.
I did this with all my middle schoolers, and they're all like, wow.
Oh, wow. Gee, he's really fast. So let's catch the quarter. Catch that quarter. I think we have one more station, Dave, the pennies.
We have Penny for your thoughts.
Penny for your thoughts. So
You
really
have one?
like a variation of the tablecloth, because I see it's getting on time here. I just want to quickly go through. So you just get some pennies onto an index card or any kind of small piece of cardboard cut out that could serve as the proverbial tablecloth, where your pennies are kind of like your table setting there. And you can make stacks of pennies to make it easier. And there you go. That's you, bud. And quickly, just like the tablecloth is removed, the card is removed, and the pennies just respond to gravity and go into the cup. All right, what's going on over there in West Lafayette, Indiana?
Yeah, we have Faith here trying to do this. Now she's stacking the pennies one on top of the other. And as you point out, the more mass, the more successful she's likely to be. We're trying nickels as well.
Right, so other coins works well. It's always good to compare and contrast. Great process, Phil. To see if more pennies is actually more successful or more easier. Did I just say that? Nickels, quarters, what's going to work? I mean, you already have quarters out for catch the quarter, so why not try them for this station as well? It doesn't only have to be pennies.
Christopher, I think
Yes.
we have one more station, and that is piece of the pie.
Yeah, do you do that? Because I do not have my piece of pie.
We have pie. And we have pie with one piece missing. Now, most students would predict that when we cut out the piece of pie out of the plate, that the marble will just jump across and continue in the circle.
Right. So that's actually, we asked them to predict what's going to happen with, we kind of demonstrate with a full plate, get the marble in motion going around the lip of the plate, the rim of the plate, and it just keeps on going around in a circle. But what happens if you take a piece of plate or pie out there and suddenly your marble has to travel around that plate? Which direction is it going to go? Actually, a lot of kids will say, "Oh, we'll just keep going around in the circle," and actually jump almost like in the movie Speed, where the bus is actually jumping across the highway. But as it turns out, this is very much like the tennis ball, where the tennis ball just goes in a straight line. So does the marble and the plate. Now, if you do this not on a table, they can actually see the marble isn't only just going, what happens to the marble if this is not on a table? Does it go immediately straight down? Does it jump across and go to the plate? Or does it move down at an angle? And it turns out that the marble moves down at an angle because it still has forward motion, but gravity, it's also responding to gravity. And so therefore it moves down at an angle. So you can do this either on a table, as Dave set up, or you can have them spinning it on their own and seeing what happens to the marble when it gets to that gap above the ground or off when it's not on a table. So Dave, I see it's 6:15 and I think our teachers probably want to wrap it up there. I think we've hit all our stations. So I just wanted to, let's go back to my sharing here. And again, in NGSS, we find that forces, Newton's laws and motion and the interaction between objects, whether something's in motion or stable, isn't in both the middle school physical science standards and in the high school physical science standards, actually almost the same, similar expressions, relevant performance expectations for both a middle school and a high school standard, although it doesn't directly say this is Newton's first law. The high school one actually goes into the second law, but first law, second law have a lot of crossover, and there is relationship between there. So we could actually, while it's not actually getting the mathematical relationship between force, mass, and acceleration, or force equals ma, we can relate the concept of motion and acceleration and change to this if we aren't happy with that. And oh, why is this there? You need to move. There we go. That core idea, forces in motion, kind of the umbrella for all of our Newton's laws would fall into all of that. And lazy days, I feel, hits these practices, science and engineering practices, carrying out an investigation. They're analyzing and interpreting data. Now, it may not be necessarily quantitative data, it may be qualitative, but they're certainly analyzing and interpreting it and using models. These are all different models in a sense to demonstrate Newton's first law, and they're constructing explanations as to why the marble behaved the way it did. Why didn't the water come out of the cup? Why did the dominoes or pennies or quarters or the cups behave the way they did? So they're trying to explain things as per Newton's first law, and all tying it to, well, it's nature's way of being lazy. It didn't want to change, or it didn't want to stop moving. It didn't want to stop its motion, or it didn't want to suddenly was made to move because there was a change. Whether how we frame this lazy days, whether we're going to spend a couple days doing these stations, we could see it as a cause and effect theme, or stability and change, or energy of matter. Any of these would work. It just depends on your interpretation of how you see lazy days and how you're framing lazy days with that, and whether you want your students to see Newton's first law as a cause and effect, and that the forces are the cause, and that there is an effect on a particular object, or as a stability and change, or energy and matter, because we're dealing with motion, objects and things that are in motion. So it would be up to you as the teacher in framing this lesson, and which cross-cutting concept you want your students to really be focused on as you go through lazy days. And because it's lazy days and there's 10 stations, I think it would be crazy to put out all 10 and have students try and get to all 10 in a particular period, or a double period, or a block schedule, simply for your sanity's sake and their time to spend at each station, and really be present and thinking about their own physical bodies and their colleagues with whom they're working, what the bodies are doing and how they're behaving, just to really get into each of those stations. And I would maybe only put out 3 stations at most. If you have a standard I don't know, 40 to 45-minute class period where you can do lazy days and you can spend 2 or 3 days on it. I would say maybe 3 stations out for them to focus on. And maybe if you can't get to all 10, you can pick whatever 5 or 6 that you want to do if you can allow 2 teaching days to do this. That's what makes it kind of nice, in that you have that option. If you don't have the time to get all 10 in over 2 or 3 days, pick which ones that you just want to focus on and gear it towards those. So the cross-cutting concept that you feel is most applicable to the way you teach, what is it about Newton's first law that you want them to get? Would be your decision. And then which of these stations do you want them to experience? Which ones do you see easiest, most accessible, and easiest for them to truly grasp what you know about Newton's first law, or what you want them to get out of Newton's first law? So, Dave, anything else?
Well, I can tell you which direction my body wants to take without any force at all, and that's to go home and have dinner. However, before we finish up, Mitch is going to come over and draw 2 names out of the jar. If we draw your name, say, unmute yourself, tell me you're here, and you will be a winner. All right, Mitch.